SPE Al-Azhar. اوكي النهارده احنا مع SPE Al-Azhar, the first student chapter of the Society of Petroleum Engineer. We was founded in June 2005 by students in the Petroleum Engineer Department. وهي منظمه non profit, وهدفها الاول والاخير ان هي بتنهانس الستودنت سكيلز وبتشير knowledge among them, وبتprovide the students all information in technical and soft skills. SPE won many awards including outstanding student chapter 2022 and outstanding student chapter also 2021. And Student Chapter Excellence Award in 2020, and lots of awards. Today, we are honored to interview Dr. Shahab Mohaghegh. He is a pioneer in the application of artificial intelligence and machine learning, especially in the exploration and the production industry. He is a professor of petroleum and natural gas engineering at West Virginia University, and the president and the COO of Intelligent Solutions. He also is the director of WVU Lead. He is SPE Distinguished Lecturer in 2017 and 2020, and he has long history and great bio, by the way. So, Dr. Shahab, please tell us more about yourself. We have passion to know more about yourself. Welcome, Dr. Shahab.
Thank you very much. Just my background is I actually moved to United States when I was 16 years old. It was 1977, and did my BS, MS, and PhD here. And when I got into West Virginia University as an assistant professor, through a process that was completely unique, actually, I got exposed to meditation. And to me, meditation was not something real. So I started doing a bit of research and understanding about it. I've learned that human brain is a very important issue here. That helps meditation, and as I started learning more and more about human brain, then I was exposed to what today is called artificial intelligence. At that time, it was not called artificial intelligence. If you like, I can tell you why and what was the history of this technology. And anyways, so starting 1991, I started working on what today is called artificial intelligence, specifically artificial neural networks and fuzzy set theory and genetic algorithm. And in the past 31 years, all my research, all my development, everything I have done is the application of this technology in oil and gas industry. I cannot hear you. I think you are muted.
I said you are our role model.
Sorry again?
You are our role model.
Thank you. You're very kind. Thank you very much.
Okay, so we can start our meeting right now by asking about what's machine learning. We want to know about what are the definitions, what's the technology. We know that it's trendy nowadays. But we can start with definition, what's machine learning and artificial intelligence in general.
Do you want me to share my screen so I can show you slides on that topic?
Okay, please do.
Okay. Let me bring this. Let me see, open participant. All right, so please let me know if you can see it.
Yes, for now.
Okay, very good. So honestly, what has happened in the past decade, specifically in oil and gas industry, one of the things that are very important is apparently a lot of people right now in the oil industry have a completely different definition of what AI is. And actually, if you want, I can show you what was done at JPT, Journal of Petroleum Technology, which is the SPE's main journal. A few months ago, they had something in that article, and the people who wrote the article, I'm not telling you the names, they provided a definition of AI and machine learning. If you want, I can show it to you, but I think you all know the JPT and you can look at it. And to be very honest, when I saw that, I was very, very, I just couldn't believe that they did that, because it makes sense that I think the definition of artificial intelligence and machine learning would be done by people who developed it many decades ago, rather than by people who are using it right now and using it differently, and then they have their own definition of that. So in that context, I think it's very important to see what actually the definition of this technology is. And again, these are not my definitions, these are the definitions of people who have generated it. So first and foremost, what is artificial intelligence? Artificial intelligence is the technology that simulates human intelligence. So natural intelligence, artificial intelligence. So artificial intelligence literally is planning to show or to model or to simulate human and natural intelligence, right? How is it doing it? It's doing it through mimicking a human brain. And it does it through analysis, modeling, and decision-making. So that sounds very simple, but that's very true. That's what artificial intelligence is. Then it's very important to understand this definition. Then you see the way it has to be used, how different it is, that as an engineer, as a scientist, you're going to use it versus people who are using it or they're using this technology as a name, really, to make money. It's a marketing thing. It's a business thing. It's not really science and technology. So that's artificial intelligence. What is machine learning? Machine learning is the science of making computers to act, one, without being explicitly programmed. That's very important. As scientists, as engineers, you know that when you write, until now, before AI and machine learning, when you write a code, for example, you do numerical reservoir simulation. What do? You tell the computers exactly what to do in so much detail. Computer doesn't do anything on its own. It does exactly what you code it to do. However, the science of making computers in machine learning is without being explicit programmed. Number one. Number two, it is done, machine learning, through using open computer algorithm and learning from data. What does that mean? That means the algorithm of machine learning it's an open algorithm, and by using that algorithm, you're not telling it exactly what to do, explicitly what to do. However, you're telling it to use the data that you are providing it. So the same algorithm can use data from multiple different ways, from multiple different types of problem solving, and it does its solution. So anyways, AI mimics nature to solve complex and dynamic problem. Homo sapien brain, our human brain, is constructed by evolution. That's one of the very, very important things that I have learned, that when you become very interested and learn so much about artificial intelligence, you become incredibly interested in evolution. And it deals with uncertainties and various possibilities. There are three algorithms that machine learning algorithms that we use in order to perform machine learning and AI. One is artificial neural network that mimics neurons in human brain, and for the learning process and learning through pattern recognition by using data to train a series of open computer algorithms. The second one is fuzzy set theory that mimics human logic, not human neurons, but human brain through the way we use logic. And that logic avoids the limitation of two-valued logic that has been used in the science and technology since 200 years ago. The two-valued logic is say yes, no, 0, 1, black, white, up, down. Our brain does not make discussion, doesn't do that. Our brain doesn't use two-valued logic. It uses unlimited number of logic. So that's what fuzzy logic is in order to expand the potential to learn and make reasonable decision based on non-exact. And finally, it has to do with genetic algorithm, which mimics Darwinian evolution theory for optimization process. And it's an evolutionary computing process that finds a solution and performs optimization to complex problems through natural selection. So these are the definitions of AI and machine learning that I can share with you. I cannot hear anything if you have sharing. Allah, if you're speaking, I think I cannot hear you because you're muted.
Yes, I am with you, Doctor. Until now, or in the past, we give the input also rule and wait the output from the computer. It's traditional programming. Okay, but now we give the computer or program input and output, and we wait for rule. That's right.
Yes, to a very large extent is correct. That's what machine learning does. The same algorithm can be used in engineering or in other technologies, but what happens, as you said, the data as input goes into it depending if you're doing supervised or unsupervised. If supervised, then yes, you have input and output for training, and it's unsupervised, you don't need any output. You just provide all the input and you let it cluster and find out what the difference is between different types of collection of the data that you have.
Oh, I think it's more powerful for now to use the. Okay, so let's know about how AI should be used to model physics.
To modeling physics, that's one of the main issues that unfortunately a lot of engineers do not realize, that there is a difference between solving engineering problem versus non-engineering problem, correct? So remember, artificial intelligence, as I said, it is going to mimic natural intelligence, human intelligence. So I have a very simple question from you guys. Think about it. You are students, you are engineers. So would it be possible for your intelligence to solve physics and engineering problems if you would not go to university and get a BS or MS or PhD in engineering? Would it be possible? No, right? So if that is true in human intelligence, in natural intelligence, wouldn't it be true for artificial intelligence? Absolutely, yes. That's why some people do not realize that. They use the same technology that was developed by Google in 2005, 2006 for image recognition later on for sound recognition, for a lot of simple thing that doesn't need, so a 5-year-old can tell which one is mom, which one is dad, right? A 5-year-old without going to school can tell if somebody calls him, can, oh, was it my dad called me or my mom called me? It has sound recognition. So sound recognition, image recognition, these requires natural, general intelligence. You do not need, as a human being, natural intelligence. You do not need to go to the university and go years of to find out which one is cat, which one is dog. Correct? A 5-year-old can do that. So the same thing is true about natural artificial intelligence. However, when you do it using computers, it's not going to be simple. Don't get me wrong. I'm not saying what IBM, Amazon, or Google does are simple. Why? Because they're general intelligence. That's not true. It's very, very hard because we tried to do that for decades. We were not able to do that until the artificial intelligence allowed to do that. However, when you're going to use your artificial intelligence to solve engineering problem, natural intelligence, general intelligence is not enough. You cannot use the convolutional neural network generated by Google for image recognition to solve engineering related problem. Unfortunately, a lot of people still do that. And the key is in order to solve engineering, scientific problems using artificial intelligence, you must have domain expertise. You must be an engineer. You must be a scientist. You must. Why? Because it's machine learning. Learning requires teaching. So your job through the data is to teach the machine learning algorithm about AI, about petroleum engineering, about mechanical engineering, about any science that you want to teach it. How do you do that? You do that through data. You cannot talk to it, you just through, and that's what's so unique about that. If you want, I can show you a few slides on that topic. Let me go ahead and share my screen again to give you a few examples of what. Okay, let me see. Why doesn't it let me do that? Oh, here it is. Okay, so here it is. Please let me know if you can see my screen.
Yes, we can see right now.
Very good. So modeling physics using AI and machine learning. The first question, can human brain address physical phenomena? You and I, all the kids, all the human beings, can we solve, can we act, or our human does solve physics-related problem, the simple ones? The answer is yes. I'll show you. You know what this is? This is rocket trajectory, where people right now with they're doing in Russia and hitting others, right? So when they do that, what is this? What is the mathematical equation for this? It's very, very simple. You find the range. You want to know where this comes down. You have to know the initial velocity. You should know the theta, the angle, and then it tells you where it comes down. So that's it's a very simple equation, but that equation tells you where that rocket comes down, or that's how, if you want to take it in a specific place, you know what to do, right? In that context, modeling physics using data rather than modeling physics through mathematical equation. So can human brain solve physics-based problem? Of course it can. You see, it's the same thing. The football in the US, they throw the ball and the guy runs and catches it. So the question is, does human brain, he's this guy who catches this ball. Same thing. I usually do that in the class. I take my something and I throw it at one of my students and I tell them to catch it, and they catch it. And I ask them, when you caught that, did your brain make this mathematical equation and solved it and then told your muscle how to move to catch what I told you? Absolutely not. The human brain does not build a mathematical equation and solve it to find out where this comes down. So does human brain construct and solve mathematical equation in order to solve physics-based problem? No. So what does it do? How does human brain solve this, what I just showed you? They do it through observation, human brain. It does it through observation, it does through learning, trial and error. It literally uses data, human brain, to do that. You see what this lady doing in this picture? This is very, very, very hard to build a mathematical equation. We can do that, but it's not easy at all to do that, to be able to, and a kid can do that. Our brain allows us to do that. Why? It does it through data, through observation. And another thing that's very important, the data that human brain uses to do all of this, the data is uncertain. It's full of noise. It's not exact, yet our brain is able to handle it. In that context, since AI mimics human brain, it can use data to solve physics-based problem. That is the case. I'm going to give you one example, actually. Can physics be modeled by data using machine learning and AI? The answer is yes. How can you prove that? Well, you build a model of highly complex physics. You solve it using a numerical solution. Then you generate the data from the numerical solution, and using only the generated data, not the mathematical equation that you built, and you model the physics using AI and machine learning. And it validates the AI model by highly complex physics that generates the data. That data allows you to solve the same problem. So anyways, I don't want to go into much detail. They're the key, folks. That's one of the major issues that a lot of people do not realize in engineering. That if you use artificial intelligence and machine learning, you're using actual measured data, not mathematically calculated data. You can do mathematically calculated data. You just do that in academia to teach the kids how to use the algorithm. But when you go out of academia, you try to use real problem, then you do not use mathematical equation to generate data. You do it actual data, measured data. Why? Because the problem, then physics problem that you solve includes no assumption, no interpretation, no simplification, no preconceived notion, and no biases. That's the key. That's the difference between solving the problem solving a reservoir engineering problem using AI versus using numerical simulation, because numerical simulation includes interpretation. It includes some assumption. Any mathematical equation of the physics, the more complex the physics is, there is more assumption, there is more interpretations that comes in. And in numerical simulation, there is simplification, for those of you who know what numerical simulations details are. So in that context, that's what I wanted to answer that question.
Yes, Doctor, you already had the target. So you told that data human proved is not certain and maybe need to clean and something like that. You remembered me with a familiar sentence: garbage in, garbage out.
Mm-hmm.
Yeah, for data. So from your talk, Doctor, we know now there are a difference between using AI to solve engineering problems and engineering issues. That's right?
Absolutely, absolutely. Absolutely. In the last sentence that you mentioned, actually, it's correct that the data, that's one of the major things that I mentioned. You need, before just taking the data, you know what the statisticians do. Statisticians take the data and put it in their algorithm, and they get the results. That's one of the major differences between AI and machine learning versus traditional statistics. Don't forget, guys, a lot of people think these are the same thing. They're not. the traditional statistics, when was it developed? 150 years ago. Why didn't do what they say they're doing it now? Number one, AI, what we work, it's only 2.5 decades, right? Number one. Number two, if one of the things you should do, study the history of AI. One of the things you learn, you know which scientists were against AI at the very, very beginning? Statisticians, because they said, oh, data-driven, we are data-driven. We've been doing it for 100. What the hell, what are you doing? You're saying AI is data-driven. So if it's data-driven, it's us. But then things changed. Google did things that was able to solve problems that the statisticians and others tried for 100 years, they couldn't do it, but they do it through AI. So that's one. Now let's talk about specifically, as you asked, engineer. I'm going to show you a couple of slides on that as well. Give me 1 second. I'm going to again share my screen with you. This is engineering application of artificial intelligence and machine learning, modeling physics based on AI and machine learning. The first thing I want to show you is actually what this new technology is. If you read the history, the evolution, what we are called Homo sapiens. We came to what today is called Middle East and Europe. Homo sapiens got out of East Africa and came to the Middle East and Europe 70,000 years ago. And that was a cognitive revolution. Why? Because it changed a lot of things. We came 70,000 years ago to where today is called Europe and Middle East. Before us, for 140,000 years, Neanderthals were there. And they were never, in that 140,000, they never changed to become very, very advanced. Look where we are. At the beginning, in 70,000 years ago, we were doing things that were very, very different from, and then it took us 60 years to come up with the revolution that was called agricultural revolution. That was 12,000 years ago. The Neanderthals never made that revolution. And that was the difference between us and them, our brain. So the agriculture, from cognitive revolution to agricultural revolution. And after that, about mid-18, we had the industrial revolution, what today is called, right? And today, we have biotech and artificial intelligence revolution that happened in mid-1980s. And this revolution, it's going to change everything in the next few decades, folks. See, industrial, as I showed you, the cognition revolution took thousands of years. Agricultural revolution to be changed took 10,000 years. This one took hundreds of thousand years. This one's going to take only a few decades, tens of years. Things are going to change completely. So application of AI and machine learning, engineering related problem solving. It requires engineering knowledge and domain expertise, number one. Number two, it requires teaching through detailed understanding and communication of the data to the machine learning algorithm. So what is the difference between engineering and non-engineering related problem? What are these differences? Are they the same? As I mentioned earlier, no, they're not the same, they're different. Solving non-engineering problems, such as image recognition, sound recognition, it only requires general intelligence. Non-engineering problem, as I said, it doesn't require any domain expertise. However, engineering problem requires domain expertise. It requires for you to be able to solve engineering related problem. Here's an example. You see, this is what happened in 2005 through Google image recognition. And you can find which ones are cats and which one is dogs. The key is a child can do that. That child doesn't need to be an engineer or go to the university to be able to do that, correct? How about face recognition? Mom versus dad, right? Your brother versus your sister. A child can do that. General intelligence can do that. Object recognition. When you say the difference between a car and a bicycle and people who are walking, do you need a bachelor's degree to do that? No, it's general intelligence. How about voice recognition? You say Siri or Alex and do all of that, but it is voice recognition. The voice recognition also requires only general intelligence. You don't need a bachelor's degree for that. Even autonomous vehicles, when the vehicle are running, my question to you is, think about it. Do you need a bachelor's degree to be able to drive a car? No, people drive a car without even being able to write or to read, but they can. So this is general intelligence, not building the car, but driving the car. In that context, and even translation, when there are kids who our father is from one, let's say the father is from Egypt and the mom is from Germany, let's say, for example, the child very soon can speak Arabic and German, both languages, the child, because it again, is general intelligence. And caption generation, these are also general intelligence. I'm not going to go into the detail of that. But anyways, most common application of AI is today's most common application is general intelligence. And this is only a pathway of AGI, the general intelligence. General intelligence does not require domain expertise. This does not mean that general intelligence is easy. It's not, it's very hard. Nevertheless, there are differences between general intelligence and domain expertise. So I'm going to give you another example. Imagine that you have this. You have dots of yellow and you have dots of black, right? And then you go to a child and say, I want to separate these black and yellow circles. How much expertise? I want you to put a line. Go to a 5-year-old, a 10-year-old, let's say, give him a pen and say, okay, can you draw a line that separates yellow from black? How much expertise do you need to do that? Not much, right? A line can, as a circle, can change that, right? Separate that. And the only thing is that line is non-linear, right? It's not linear. So what if you require that separation? You want to separate black and yellow, but you want it to be straight line, a linear line. Now, can still a 5-year-old to do that? Or do you need to know mathematics to do that? And can a 5-year-old do this? Do you need any type of expertise to do this? Yes, you need mathematics expertise to do that. How? You take that, you solve an engineering problem, and then a straight line separates them. You see, that's the difference between general intelligence and non-general intelligence. And that's the whole idea that you go, if it's non-linear, so one last thing I want to say, share with you. First, let me show you something. What do you think if a company comes and says, we can create master reservoir engineers in just 1 month, no matter what you are in the back? You are, let's say, you're a doctor in medicine, right? Do you believe that in 1 month they can make a master? How about master petroleum engineer in just 1 month? Is that possible? Does any company, or master mechanical engineer in 1 month? I just made this up. There is nobody, no company that says that. But does it make sense to you? Obviously not. This is not real. No company has ever done such a marketing thing. Now, but let me show you something else. This is true. I didn't make this. This is a real marketing advertisement. They say they're going to make a master data scientist in just 1 month. That's why, unfortunately, AI and machine learning has become literally not a science and technology. To a very large extent, people use it or they try to make money out of it, nothing real. So anyways, I'm going to stop here and answer any question you have.
Doctor, there are many scientists who said we can't reach to general AI. We still in narrow AI, and we will be in narrow AI even if in the future. So what's your opinion about this point?
One of the things I strongly believe is that actually you need to learn natural AI, general AI. Learn everything that have been done by experts in AI who solved these problems that I showed you: voice recognition, image recognition, all of that things that I showed you, a lot of them. But keep one thing in mind. The reason you need to get exposed to that, because in order to be able to use AI in engineering, you have to be an engineering domain expert, but then you have to become an AI domain expert. So I always tell my students, I make them go and study CNN, the convolutional neural network, or LSTM, all of these things that Google and IBM make. I tell them, go learn what they have done. The only thing I tell them also is do not use exactly what they have done to solve engineering related problem, because if you do that, you can never solve engineering problem. What you need to do is to learn from what they have done. Why? Because they are AI experts. Learn how, with the problem they were trying to solve, what did they do? What did they learn? How did they use AI to solve the problem? Since the problem you're solving is very different, you have to learn the way they approach the solution, not exactly the technology that they use. Come back and do the same thing in your own case. This is what you mentioned, and I said earlier that you are very correct, how to deal with the data. So I'll give you an example. When you use actual data to solve reservoir engineering, right? The question is, there are two issues, actually three issues. Number one, the data, not all of the data exactly is perfect, right? There are some issues with it, as you mentioned. So number one thing you need to do, you need to study that data that was given to you from the reservoir engineer, the actual data. What we call, actually, if you want, one day I can give you a presentation on AI-based reservoir modeling, reservoir simulation and modeling that we have generated it right now. So when the first thing we do, we call it well biography. What does that mean? That means we take all the data for every single well and we plot it in all the detail and try to see from a reservoir engineering point of view, does that make sense? What is it that some of this data, usually 90% of it makes sense, 95% of it makes sense, but there are issues in that data that you have to figure out, does it make sense if the production is going down and all of a sudden goes up and comes down, because the production is never like this. It's always like this, right? So when you look at that, you have, for a reservoir engineer, you plot the oil production, gas production, water production, wellhead pressure, choke setting, completion, everything that has been done, that you have the data, plot up all together and see if the production moves. Does that make sense? Anything else has moved? Anything else has been done for that to happen? If the answer is yes, it's actually fantastic, because this is how you teach the machine learning algorithm. But when something doesn't make any sense to you, you immediately don't remove it, but that gives you option to concentrate on that. Maybe you have to find out that's an outlier, that you have to take care of it. When it's very different from, let's assume you have 100 wells in your reservoir, and you have 6, 7, 10 years of production. You have a lot of data. Take all that data and plot it, and then 98% of it tells you it did very, very good. Can you find out? So literally, you're going to spend a lot of time on identifying that data to figure out how to handle it, how to take that data and teach reservoir engineering to machine learning algorithm. That's number one. What is number two? Number two is always some data is missing. Always some, keep one thing in mind, the data has been collected, measured by human being in the past several years, right? Is it possible that they made mistakes? Or of course they did. So is it possible that for some reason, for 1 week, you don't have the data? For, let's say, wellhead pressure was not measured in three months? Yes. Now, what are you going to do with it? So first, you identify all the missing data. One thing you never should do, and almost every company right now, Schlumberger or any other vendors that take money from an oil company to do AI. You know what they do when they do that? They use mathematical equation to generate data to put it in there. That's very, very, very wrong. You must not do it. And if you have any question why, I'll give you a lot of detail on that. But how do you do that? How do you handle it? You actually use artificial intelligence to generate the data that it's missing using all the data that's available. It learns from all the data and it says, okay, given this fact, and it generates that data, and you have to validate that. I'll explain that if you want in the reservoir engineering, not necessarily here. And finally, the third one is this is the incredibly important that a lot of these Schlumbergers and other companies do not do. I have a question for you. As a reservoir engineer, what do you learn? Is everything that a well, let's say a field, you have 100 wells, right? Take one of the wells. What happens to that well? The oil, gas, water production that comes out, the pressure changes that takes place in that well. Question. Is it only about that well? No, it has to do the offset wells around it, offset producers, offset injectors, right? So in other words, everything happens to a single well. It has to do the wells around it too. Depends how close they are. It's a function of time, because if you're looking at this particular well number 8, this well number 8, during the first 2 years, there was no well close to it. But then later on, they drilled the wells closer to it, then they communicated, they interacted, right? Offset well. Question, shouldn't you tell that to the machine learning algorithm and bring all that information together? And given the fact that fluid flow through porous media is a function of space and time, right? So you have to talk about the geology. And this is what we learned as petroleum engineers. This is what you learn as when you work in a company. All of that, that's why it's so incredibly important for you to be a domain expert. You have to bring all that, because as you mentioned earlier, you have to spend literally more than 50% of your time to prepare the data, actually generate what we call feature generation, to teach, using that data to teach the machine learning algorithm. So these are incredibly important in engineering problems.
So right now we have big data or very large of data, but dealing with data is not easy. It needs time and knowledge how to fill missing the data or pre-processing the data, by the way.
Exactly.
Okay, it's awesome, doctor. So now, before talking especially about machine learning in oil and gas, we would like to know, in the last question you mentioned computer vision, object detection, and something like that. So we wanna like to know what's the big difference between ML and deep learning. We also lesson the terminology of deep learning. So what's the difference between machine learning and deep learning?
Actually, deep learning is a machine learning algorithm. What deep learning is, if you go back to the history of artificial neural network, it really started in 1955. However, at that time, it used only feed-forward modeling, and it only used 2 layers of input and output. Then in 1969, 2 professors, one from Stanford, the other one, I don't remember where he was from, they wrote a paper, they wrote a book. The book was called Perceptron. It was published in 1969. In that, they proved that artificial neural network, when it will not work and it's wrong, and the only problem it can solve, it's linear. And they were absolutely correct, mathematically proved it. They were absolutely correct because it was only 2-layer input and output, and it was only feed-forward. What that happened is that's why at that time what was called artificial intelligence included 2 areas: rule-based system, data-driven system. Because that artificial neural network was data-driven and they wrote this book, data-driven went out. And artificial intelligence was all about rules, 2-valued, of course, rules, right? And anyways, then all the money, tens, hundreds of millions of dollars of grant for research went to artificial intelligence, which was all about rules, had nothing to do with data based on what happened in 1969, that book, right? This happened, and that artificial intelligence that had to do with rules didn't do anything, didn't solve any problem. With hundreds of millions of dollars and decades of research. That is why in 1986, when the new version of artificial neural network started, backpropagation algorithm. So what happened, instead of being 2 layers, input and output, they added another layer in the middle. They call it hidden neurons. Number 1. Number 2, it was not only feed-forward, but it had feed-forward and backward. So it went back and forth. That's that algorithm. That came, it changed everything. It literally undo what was written in that book in Perceptron. It understood it and it solved it. 1986. At that time, nobody ever called it artificial intelligence. They called it computational intelligence. They called it virtual intelligence. They called it soft compute. They called it so many names, but not artificial intelligence. Why? Because the word artificial intelligence since 50s, hundreds of millions didn't do anything. Why? It was only rule-based. Now it became data-based. It went on all the way to 2005 when Google started doing that image recognition, sound recognition. Then they start calling it artificial intelligence, since a lot of people didn't know what happened in the past, that word was okay. Now it's called artificial intelligence. So the key about this is that, excuse me. Now, you asked about machine learning and deep learning. Generally, machine learning are the algorithms that allows artificial intelligence to happen. Prior to that, the first version of the neural network had only 1 layer, hidden layer, right? But one of the things that Google did in doing their image recognition in 2005, 2006, what they did, they generated 15 layers between input and output. That's why it's called deep learning. But keep one thing in mind, out of those 15, about 11 of them had nothing to do with artificial neural network. That was data that's what they call it, convolutional. They took the face. In the first layer, they only identified the points that are like this. Then in the second, the point that was like this, then like this. And then after 15 times doing that, that's a different technology. It's called, I can tell you what the name is. That was a statistical thing that they had done. And then they convolve it. They put them all together. Which one is this? Which one is this? Which one is this? And they put them together. Then they have several layers, hidden layers. And that's what they call a deep learning. That's what deep learning started. Deep learning is a neural network that doesn't have only one hidden layer, but it could have multiple hidden layers. Is that good? Yes, it's great. And does it absolutely require? No. There's a lot of problems you can solve with one layer, and there's many of them you can use. And that's one of the research that I ask all my kids to do when they want to solve engineering related problem. They start with one layer and then they go, and when they add more layers, it gets better and it shows you how this whole thing is working. I hope that answers your question.
Yeah, it's clear enough. And so from one hidden layers to 50 hidden layers, there are many dollars and time spent to know that. We had at the past only feed forward or closed form training, but now we have a back propagation, which is more powerful. That's amazing, Doctor. So by all this data and all the knowledge, how can we avoid the bias in the machine learning model toward the religion, sex, nationality, even color? How we can reach those?
That's a very, very good question. It's incredibly important, actually. And unfortunately, a lot of engineers don't pay attention to that. But it's so true, and it's so incredibly important. Let me show you a few slides on that. Let me share my screen with you. Please let me know if you can see it. Can you see my screen now?
Yeah, it's clear. You can go.
Yes, it's called Ethics of Artificial Intelligence, or AI ethics. So what is that? Some of the non-engineering and mainly business application of AI have impacts on people. Technologies such as facial recognition, voice recognition, human resources, bank loans. AI-based models are vulnerable to assumptions and to bias that can be introduced by its human creator through the data that is used to train and use the AI system. IBM, Google, Amazon, many of these, they have made efforts to research and address what is the bias in AI model. One solution to address bias is to create documentation for the data used, that the data that you use to train the system. Here's the, now, because of literally what happened, as you mentioned, Ella, in the past decade, these companies created incredible amount of AI models that created sexism, that created racism. The key is they didn't do it intentionally. They did it unintentional, but they found out the AI system is very racist, is very sexist, differentiates big time between men and women, or between black and white and all that. Then MIT, Massachusetts Institute of Technology, created a whole institute. They do AI ethics. They do incredible amount of research, and they found out that the problem of bias in machine learning, in the machine learning algorithm, is likely to become more significant as the technology spreads to critical areas like medicine and law. And of course, as you see, this engineering, I added it to their statement, not there, and engineering. And as more people without deep technical understanding, see, that's exactly what I said, domain expertise I've been saying for a decade, are tasked with deploying it. So some experts warn, this is what MIT says, some experts warn that algorithms, as algorithmic bias is already pervasive in many industries, and that almost no one is making an effort to identify or to correct it. However, many industries, specifically in the engineering folks, in engineering, this is happening so much. One last, this is again said by Will King, which is the MIT Technology Review. He says, Google's AI chief says, forget Elon Musk's killer robots and worry about bias in AI system instead. Because if you cannot solve this now, how in the world are you going to worry about the problem far away from us? So what is the ethics of AI in petroleum engineering? That's the key. And unfortunately, a lot of engineers do not pay attention to that. As you noted, AI ethics is the inclusion of assumption and bias in the AI-based modeling through adding data that model can generate results a certain fashion. Let me ask you a question. Think about a very complex or very easy mathematical equation. Let's assume it has 5, 10, 2, any number of variables in it, this mathematical equation. I have a very simple question from you. Those variables inside that mathematical equation, don't they correlate with one another? Of course they do, because if you don't think, all you have to do, just generate data and look, they look exactly, you can find out when permeability increases, production increases, for example, right? So when you generate data from a mathematical equation, it doesn't matter what mathematical equation it is, but it's a mathematical equation. When you generate data from that, what are you creating? You're creating an assumption. You're creating a correlation. You are telling AI what to do. This is the characteristics, right? Do you think the same thing can be done outside of bank loans, human resources, facial recognition, voice recognition? Of course it can be done. It is possible to add data in AI model in engineering in order to make AI model to do what I want, what you want, positive or negative, it doesn't matter. So in the context of AI ethics, inclusion of assumption and biases in petroleum industry is done through what they call hybrid model. All Schlumberger, all of these companies, vendors, they do a hybrid model. Why? Because why do they do that? Because they use actual data from reservoir. They cannot solve it and build a reservoir simulation. That's when it doesn't work for them. What they do, they add mathematical data to it. It's hybrid, actual and mathematical. That's what they call hybrid. Then they literally tell AI what to do. That is the problem with it. And I'm going to show you an example in a second. When data generates through mathematical equation and it's combined with actual field measurement to train AI-based model, this means A, they tried to build AI-based model only through field measurement, actual data, and they were not successful. That's why, therefore, they would generate data from a mathematical equation that include assumption and biases and combine it with actual data in their machine learning algorithm. So this hybrid model, right? Let me show you something. This hybrid model that they make, it means combining two different elements. Hybrid model means modeling through combination of two different types of modeling. Combination of AI-based model and traditional physics-based model. This want to combine these two. When hybrid model refers to combination of AI-based modeling of physics and traditional physics-based model, it's the main problem. Much worse than data assimilation that they use as history matching. Then hybrid model would be the main ethics in engineering. Why? Let me show you. AI-based modeling is purely based on fact and reality through actual measurement. Traditional physics-based model includes some of the following items in mathematical equation. It includes assumption, interpretation, preconceived notion. It can include biases. By including data from mathematical equation to actual data, you are telling AI-based what to do. Here's an example, folks. You see these? These are actual data. You see how all the way there, this is not simple. This is actually from an offshore field in Southeast Asia that we did a project for them. This is actual data. Y-axis always in oil production. X-axis here is gas lift. Here is completion. Here is porosity. Look at the data, okay? This is a conventional mature field, oil production versus porosity completion, right? I'm going to show you more data. This is onshore field in Marcellus Shale in Pennsylvania, here in the United States, in shale. Again, y-axis is it's unconventional. Y-axis is gas production. Here you have stimulated lateral length. You have number of stages and number of proppants. Remember, I showed you the data, this data. Now I'm going to give you. Let's assume you have this data. If this data is what you have, the object is to use this data to develop an AI-based model, right? When you do that, if you are successful, then you're done. But if you are non-successful, what do? What do? You do a hybrid model. How do you do that? You use mathematical equation to generate data. You combine actual data with the mathematical data. Look, this is the data that you generate from mathematical equation. You add it to this, and then you add it, and you add it, and you add it, and you add it. Look, you got this one. Now you can solve it. Now you can use the same data. This time, you can add it differently. You use a different mathematical equation. Your friends use different mathematical equation to exactly the same data and gets this one. So look, you can tell for exactly the same data. If you use hybrid model, you can tell it that exact data should be this one or it should be this one. That is the bias that can come to mathematical equation. Okay, I hope that answers your question.
Yeah, we already did, Doctor. So finally, bias, we told the model what to do. So I think bias has many problems, even if in general, like deepfake, it's a very harmful application, even if in petroleum and gas. So now we would like to speak more specific in petroleum and gas. We would like to know why using ML in petroleum, or how AI can use in reservoir simulation.
That's not easy for me to mention it because I worked about 15 years on that. And it's very hard to say it in a few sentences. I don't know if you know or not, I wrote a book called Data-Driven Reservoir Modeling. Let me show it to you. And this book actually was published by SPE, Society of Petroleum Engineers. This is right here, okay? So this explains how AI and machine learning should be used in reservoir engineering. In reservoir engineering, but the key is you have to go back. How did we do reservoir engineering? Number one, in order to be able to do this, use AI and machine learning in reservoir engineering, you must you must be a reservoir engineer. You must have very good understanding of reservoir engineering. Otherwise, it's impossible to do it. Why? Because literally, you're teaching the algorithm reservoir engineering. How do you do that? Well, I mentioned it to you a little bit at the beginning, which is you spend a lot of time studying the data, making sure every data, because that data you're providing it to the machine learning algorithm, make sure that data is correct, but you do feature generation. That feature generation doesn't mean that you're going to generate mathematical equation and generate data. That's not what I mean at all. What I mean is, for example, you come up with the idea that, okay, first and foremost, you have to identify what the problem that you're solving. What do you want as an outcome, as an output? What do you want as the results? In numerical reservoir simulation, what is your results? What do you want to do? Number one, you want to enhance production, right? Because the companies make more oil. If you have the same field, let's assume that if you have a field, you give it to one company versus another company. One company can go to that field and do a recovery in 10 years, do 70% recovery, right? And the other company would have gone, it would go in 10 years, it would do 50% recovery. What does that mean? That means there's a difference between these two companies understanding how to apply reservoir engineering and increase production. So that's the objective, to increase production, right? So increase production, what do you have to do? Well, first and foremost, everything I'm saying is what the numerical reservoir simulation does. Because literally, we are going in reservoir simulation, but not doing it numerically. We're doing it AI-based. In numerical reservoir simulation, we have a complex mathematical equation called, it's a space and time related, but it's so complex and it cannot be solved analytically. It has to be solved numerically. That's why numerical simulation is generated, built. So it takes it in cells and then time steps. And the objective is, first, it has to match all the past 10 years. Because if it matches it well, then you can believe what it says in the future. But if the model cannot tell you what happened in the past, then how could you believe what it's going to tell you in the future? It's going to be wrong, unless let's call it history matching, right? But the problem is, how do you make history matching in numerical reservoir simulation as a reservoir engineer? For those of you guys, I don't know, the people in this conversation right now, they're students or engineers who do reservoir engineering?
They are petroleum engineers.
Okay. Petroleum
undergraduated, and also there are engineers who are graduated.
Very good. So I'm going to say it to both of them. So once you learn numerical reservoir simulation in your master's degree in petroleum engineering, when you go and start working for a company and they ask you to do numerical simulation, the first thing you have to do is history matching. Do you know, if for those of you who are not sure, ask those engineers that are there that have experience, they can tell you that how long does it take them to do history matching? 1 day, 1 week, 1 month, 1 year? Nobody knows. Literally, it has to do with how many weeks or month you are given. If you're given 2 weeks, that's going to take you 2 weeks to do it. Are you done? Of course not. If you give me another 2 weeks, I can do better. If you give me another 2 months, I can do better. If you give me you see, that's the key. And how do they do that? How do reservoir engineers start doing numerical simulation in order to do history matching? Well, what they do, they don't start. Who started? The ones who started is a geological expert. the geologists and geophysicists and petrophysicists, those people first build a geological model based on the data that they have. And then they give it to the reservoir engineer. Reservoir engineers take that geological model, puts it into the numerical reservoir simulation. And in the past 70 years, folks, every company in the world, let's assume, has done this 10 million times. Not even once in the 70 years before, not even once in the 10 million numerical reservoir simulation, the geological model that was provided to a reservoir engineer and put into the numerical reservoir simulation, it automatically gives you a history match. Never, ever happened. So what you do as a reservoir engineer, you take that geological model and you start changing it. And it depends what you use. If you use CMG, if you use at the university, in my classes in the first course, I make the kids do their own, of course, but they have to use the commercial one when they work for a company. When you use Eclipse or T-Navigator or any commercial numerical simulator, what they do not tell you that I'm going to change the measured porosity and permeability of this well to get a history match. But they're doing it. You know how they do it? They change the transmissibility around the wells. When you click and you change that, what is changing? What is transmissibility? Transmissibility is pressure. It's porosity and permeability and thickness about all the cells around it. So you are not directly changing it, but indirectly you're changing it. So literally in history matching, you change the numerical, the geological model in order to get the history match. It's going to take a long time for you to do that, but you can do that. You do that on a well by well basis, right? What do you do in numerical reservoir? What do you do in AI based? You don't do that. You do it exactly the opposite. How? You don't start with a geological model. You start with actual data. You start with production, oil production, gas production, water production, wellhead pressure, water choke setting, flow line pressure. Why? Because in the numerical simulation, in that equation, they have flow line pressure. We have the pressure that we need is at the bottom of the reservoir, of the well at the reservoir is. That is hardly ever measured. That's why 30 years ago, 35 years ago, in University of Tulsa, they created another series of mathematical equation that takes the wellhead pressure and tells you what the pressure downhole pressure is. And you need downhole pressure in order to do numerical simulation work. In AI-based, you don't. Why? Because no, it was never measured. You only have to use that's measured. In AI-based, you use, it's a reservoir and well-based combination. So what you do, you literally, there is a thing called, we developed it, maybe in a different situation, I can give you a whole presentation. It's going to take at least 1 hour, maybe even more, to show you the details of this technology, that we generate what we call geoanalytics. We create geological model based on facts that has to do with actual what happened in the top, and then you history match immediately every single well. You have 100 wells for 10 years, so you history match the whole thing. And one more thing you do in AI that we don't used to do it in numerical simulation, we no longer do it, is let's assume they give you a field right now. Today is what? Today is August 2022, right? And let's assume that it worked. They give you data for 10 years from 2010, right? The first thing you have to do, they give you the data up to August of 2022. right? The first thing you have to do is you say, okay, this is not August of 2022. Let's assume we are in January of 2020. What does that mean? That means from January 2020 to August 2022, you have the data. You know exactly what happened, but let's assume we're not there. So take that, all the data from January 2020 until August 2022, cut it and put it out. Only use the data from the 2010 to 2020, 10 years of the data. Use that data, do a history match, do everything that we say AI-based. And the objective is you have to forecast, because when you do this, let's say a company gives you this, the company that gives you this in August 2022, what are they going to do? They're going to forecast what happens in 2023, 2024, 2025. Isn't that true? That's what you want to do, because if you can forecast it, then you can optimize it to increase production. So first you do, in order to be able to do that, you say, okay, it's 2020, it is 2020, I'm sorry. I have 2 years of the data that I'm not going to use to build the model. But once I build the model, I'm going to forecast this 2 years. If I'm correct, then I can trust it and give it back to the company and said, here, look, I took the data for that 10 years. I forecasted this 2 years and I didn't use the data. But look how good, within 10% accuracy I can, then you can trust what I will tell you in the past. This is what we do actually. And then once we do that, so the entire, the process is called AI-based top-down modeling. Top-down modeling instead of bottom-up modeling. And that's what we do is we show the company that AI can build a reservoir simulation purely based on data, without any assumption, any interpretation, all about fact and reality, and it can forecast. And if you trust that forecast, then we can tell you how to increase production, what to inject, where to inject, if you drill a new well, where you should drill it, all that results that you get from numerical reservoir simulation, now you can get from AI-based reservoir simulator.
It was very interesting, Doctor. First of all, about data-driven book, is it provide on Amazon or anything, so we can
yes, it is provided in Amazon. It's provided also at SPE, Society of Petroleum Engineers. You're all part of it. And if you want, I can actually, SPE made a just 2 minutes conversation with me. There is a video. They asked me talk a little bit about it. I did, and I can send you a link if you want to see that as well.
Yeah, I think all of us need to have this version of this book. Yeah.
Sure.
So now we would like to know more about application AI and ML in geology and survey.
Yeah, that's
also okay.
Yeah, that's also very, very, very interesting. And again, it requires expertise. That's what I call geoanalytics. Because literally that's part of, as in petroleum engineering, whatever geological things that happen is because of the oil production, and that's that they do it. They provide it to others to build the numerical reservoir simulation. And this geoanalytics, which creates AI-based model, there is one difference between it and the way geological model has been done so far. What is the difference? Let me explain it in a short fashion, and I can show you results actually if you're interested. Okay, let me make it very simple. When geologists, geophysicists, petrophysicists, when they want to build the geological model, what data do they use? They use well logs, they use cores, they use seismic, right? And keep one thing in mind. When they do that, at the end, they give it to numerical reservoir simulators, to reservoir engineers, to us. When we use numerical reservoir simulation, what do we need from them? Do we need seismic? No. The seismic data doesn't go to numerical reservoir simulation. Do we need the actual well logs? No. The well logs don't go into the numerical reservoir simulation. Do we need cores? No, those don't go directly. So their job is to take their understanding of these and come up with value of porosity and permeability and thickness and give it to numerical and build a geological model and give it to reservoir engineers to use it in numerical reservoir simulation. But folks, let's think for 1 second. Let's say you have a well here and you have a well here. And in these two wells, when you build a geological model, the data that you have for everything regarding core and thing, you have it for this well right here, because you do it through cores, the rock that you bring forward and you measure things and you do take it to the laboratory and do all the things. Where that core rock came from that well, right? And when you do well logs measures what? Measures only 6 inches away from the well, not yards and meters. So when you have these two wells, you measure porosity and let's say permeability through all that for this particular well and for this particular well. But what's between them? The way the geologists do it, they say, okay, this is the well, this is the well. If this is 10, if the porosity I calculated here is 10 and the porosity I calculated here is 20, then what's in the middle? 15, right? 10 to 20, right in the middle. They call that spatial interpolation. They interpolate between the wells, the values, spatially, based on space. Correct? However, fluid flow in porous media, is that only about space? It's space and time. Okay, what does that mean? That means these two porosities are measured, are correct, no doubt about it, you never change it. But the porosity in the middle, we didn't measure it. We are interpreting it. We are not literally, we are measuring it between 10 and 15. 10 and 20, in the middle should be 15. So especially based on a space, we are interpolating it. But how about time? How does time play? Now, let me give you another example. Let's say this is one well, this is well 2, this is well 3. This is 10, this is 20, that one is also 20, right? So these two are 20, this is 10. So between these two is 15, between those two is 15, between those 20 is 20, right? Now, what happens, let's assume in the same field that we talked about, that 10 years you have produced, right? What happens if you take all the time-related data from these 3 wells and compare with one another? What if you say between these 2 wells, if you plot all the historical data of this well versus this well, you get a 45 degrees. That means what? No matter what the production is, this could be hundreds, it could be 200s, doesn't matter. But the change of the production in this and this is the same way. In other words, they did not interact, or they did not change each other. That's one. How about this one and the other one? That one also 22. You plot those 2 against each other, you see completely different. What does that tell you? That tells you then that the geology between these 2 is different from geology between these 2. You cannot use exactly the same. So that's what AI does for you. What AI does, it tells you between these 2 and between these 2, don't use only space. Use space and time. See how time did it? That tells you how to interpolate, or not interpolate, how to distribute these measurements. But when you do that, that's one item. Another item is to use seismic also to do that for you. beside the data. The key is in numerical reservoir simulation, you cannot do that because seismic data doesn't go, seismic and time-related data doesn't go to help the geology. In numerical in AI-based reservoir simulation, the geology is based AI development, and that's how it uses time and space. And that gives you a better distribution of reservoir characteristics. That's why when you, through AI, tell them to drill next well where, you get a much better outcome than you do with numerical simulation.
More than we want to know about this point. So about another point, how AI and ML treat in production optimization and drilling operations. How AI can optimize these 2 points?
Okay, so they're completely different, and you definitely need for production, you need production and reservoir engineers expert. For drilling, you need drilling expert. So we have done that for drilling as well. We brought in drilling expert to work with us to do that. And let's go first to the reservoir and production, because production comes from reservoir. Production has, see, the thing is, production, it's not only a function of the well and the completion and the surface facility, and all, definitely is a function of those, no doubt about it, but the reservoir also plays a role. So for production optimization, you have to take all of that. That's the difference between AI-based modeling of production optimization and numerical reservoir simulation, because we bring everything together. And as I mentioned, first and foremost, in order to be able to enhance production or optimize production, first, you have to do correct history matching, number one. Number two, you have to validate the forecast. You have to prove your forecast is correct. Number two, once you do that, then you have to generate a completely new geological model, as I mentioned, and then you use all the surface facility issues as well, which is, as I mentioned, wellhead pressure, wellhead temperature, a choke setting, and flow line pressure. All of that plays very, very important role to tell you. And also, if you're using artificial lift, such as ESP or such as gas lift, all of that data is used in this complete modeling of AI in order to tell you how you can enhance. Because if you have all that as input in your numerical reservoir, in your AI-based simulation, when you have all that as input and output is production, then you can use modification of this. And by the way, the AI-based optimization that we use is called genetic algorithm, which uses Darwinian evolution theory in order to do optimization. That's literally how we became Homo sapiens, through evolution. That's literally what you want to do. You use evolution and to change the production to find out how it enhances and goes high. That's for production. For drilling, you need data from MWF and LWF. That's big data. By the way, numerical reservoir simulation is not big data. It's a lot of data, but it's not big data. It's millions, actually hundreds of millions. And that you can get it from, and there's, by the way, from AI point, solving big data, but solving non-big data are not exactly the same. They give you a lot of interaction to deal with it. But with big data, we have done, I can show it to you in different presentation, that we've been able to identify non-productive time that takes place during drilling. And that usually takes place because the stuck takes place. Stucking, the stuck pipe that takes place, it happens either during you are drilling or during you are moving the the drilling bill. And then that's why you can actually enhance and identify how to handle that, to predict such a thing that's going to happen earlier than it's going to happen in space and time again. And again, it's you can definitely use it. We have used it, but I have to explain it in a lot more detail and show you what we have done.
Okay, as you see, there are many achievements from AI and machine learning and many topics in oil and gas, and I think it's more helpful and powerful. So now we would like to know how can machine learning used to improve future operations and prevent a repeat failure?
Prevent?
A repeat failure.
Okay. To be very honest, it's very tough to answer that question. There's no way you can say that you always do that. You repeat the failure. One of the things that's going to happen, as I said, you can use what's called evolutionary computing. One of key parts of it is genetic algorithm that we use, but there are other evolutionary computing as well in AI. So you can use that in order to identify what's going to happen in the future. But then a lot of time, what's going to happen in the future, I give you an example. We just did a project for a company in Southeast Asia, and they said, okay, when we built all the model for them, we history matched it, we call blind validation, as I mentioned. We remove some of the data that they give us and we forecast it and we compare it. And then when that works, then we know our model is good and we can go ahead and forecasting. And when we do that, then we forecasted what's going to happen in the next year if you do production. However, when we did that, we told them that in this forecast production of how much you're going to produce oil, gas, and water in the next year, what is the function of? It's a function of completion. It's a function of wellhead pressure and temperature, choke setting, and flow line pressure, and you're not drilling new wells close to it, right? Because if you change that, then our forecast is not correct. And literally what we did, for the forecast, we had to come up with, okay, wellhead pressure, we have to come up with, because there are two things. One is forecast, second is optimization. The forecast we want to do, say, okay, what would be your wellhead pressure? They say, we don't know. They say, what's going to be your choke setting? What's going to be your flow line pressure? They say, we don't know. So, okay, what we're going to do, and we tell them, and they agreed, said, we're going to use the last 6 months of your wellhead pressure, the last 6 months of wellhead temperature, all of that, we're going to average it and say the same thing is going to happen in the next year, right? And we did that, and we gave them a forecast. And then when they did the forecast for a year and they came back to us, he said, okay, several wells that you did was fantastic forecast, but a few wells that you did was not very good forecast. And we said, wow, fantastic. I'm very happy that you shared that with us. But can I ask you, what is the wellhead pressure and saturation and all those data, input data that you use for all the wells? And they said, oh, by the way, for some of the wells, the wellhead pressure was not the same that you put in there. I said, then that we didn't forecast for those something. So you see what I'm saying? And another beautiful thing about this technology, AI-based reservoir modeling that does all of that forecasting, is that you literally, we have a software actually that we share with people, and hopefully we are seriously thinking about it to share that even with the universities very soon. Not yet, but we will. That's something we're going to go up. But anyways, in that software, you can enhance the complete model literally in days, so quickly. it retrains itself every piece of data that comes in. So it is not something that you have to forecast only for, you do forecast for a long time, but you enhance it literally on a weekly basis, on a monthly basis, as new data comes in and you change things. So once you do that forecast, then you say, okay, look, if this is the wellhead pressure and wellhead saturation and wellhead choke setting and flow line pressure, and you didn't change the completion, this is going to be the forecast. However, if you want to produce more, this is what you have to do. We want to go to the optimization, evolutionary optimization technology, and we say, oh, if with this particular well, increase the wellhead to this pressure, or I'm sorry, increase the wellhead pressure, bring it down, change the choke setting to cis, flow line pressure should be changed in this. But the key is surface facility, they have limitation of what they can do. So you have to communicate with them what is possible for you to do, and you bring it in and you tell them how to change it. That's number one. Number two, because of this done you have for the entire field, you can tell them where to drill in order to get the highest amount of pressure. Because with geoanalytics, you ask about geology. One of the things it tells you, not only original oil in place, but it allows you to see the original oil in place that you have when you produce it, where it's coming from and where the other oil is left and where the pressure is left. Based on that, you can identify where to drill. And we actually, in my next presentation, if you want me to do a numerical simulation, I show you one example. We have a lot of examples, but we cannot share it with anybody. But one example is a company management in ATCE in 2020. He was a panelist, and they were asked him about AI, and he showed, he didn't tell our name, by the way, but he said we did AI, and he showed the difference between an AI-based well location versus 3 wells close to that was with numerical reservoir simulation. And it showed the difference, but how they produced. The AI produced a lot, the AI-based well produced a lot more than the other one, based on the geology. I asked him, is it possible I take your presentation and I show others? And he said yes, because it's already been done. So I can show that as well. And there are other things that we do have from several companies that they allowed us to share the results with people. I can share with you to see how AI can help enhance production.
After talking about machine learning in oil and gas and all this information, here in the chat, our engineers would like to know how to balance between studying ML and going on their study as a petroleum engineer. How can they start, and where can they find end-to-end projects, Doctor, to implement what they already know?
Yeah, that's a very, very good question, actually. The only thing you have to keep in mind is it's going to take a good amount of time for you to become an expert in AI. Keep one thing in mind. If it took you 10 years to become an expert in reservoir engineer, believe me, it's going to take you the same amount to be as expert in AI in the same. So don't think that is not a good thing. It's a fantastic thing. So, and the future of your petroleum engineering must have the AI part. So start doing it. The only thing I'm telling you as an engineer, don't think, please, do not think just because you know the algorithm of machine learning, the mathematics of it, then you are done. You know everything. That's not true. It requires a lot of research. It requires a lot of experience. It requires a lot of up and down and up and down. The more you do, the better you get. The more you do, the better you get. And keep learning. Keep learning about the history. Keep learning about ethics. Keep learning about anything that has to do with human brain. That's one of the fantastic things about AI that makes you incredibly interested about human brain. To be honest, one of the things I spend most of my time right now to learn is neuroscience and philosophy, because these are, what is AI? AI, to a very large extent, has to do with philosophy. It has a lot to do with how human brain works, the neurons in human brain, all these things that you learn about neuroscience, it makes you better about AI. That's why the difference is not about only mathematics. Please keep that in mind. But the thing is, you have to get exposed to courses and do a lot of research. And to be very honest, I'm very, very happy. I do teach a lot of these courses for SPE online, not online, sorry. I do online as well, but during the COVID, I did online, but I do it a lot in person. I like to do it a lot more in person than in any other shape, because there's a lot about interaction and communication between the people who are listening to you and have a lot of questions. And it's very important to make sure that they understand what you are telling to them. And the key is one thing: it is science. It is science. It is science. It's technology. It is not a business. It's not marketing. And those who use it in that technology, unfortunately, overwhelming majority use it in that technology, in that area. That's very, very not good, unfortunately. But yeah, get exposed to it. Get exposed to it as much as you can.
So who want a big salary, don't just go to AI, as it requires time and effort. It's science, not...
Exactly.
Okay. So, Doctor, if we know how to implement end-to-end projects and spend time or years to know machine learning, we would like to know, how can we find data to apply an ML algorithm, as data is confidential at the companies, and almost it's hard to get to bracket the project.
You are absolutely correct. And that has been my problem for the past 25 years. And to be very honest, the way I became, one of the reasons I created a consulting company was to be able to consult actual companies, and they will give me the actual data. And of course, I sign NDA. I do not share that data with anybody. But if I didn't have that actual data, it would be absolutely impossible for me to learn it. So what you just said is absolutely correct. However, I came up with one idea, because I teach at the university, and the most important to me is to teach AI and machine learning to my students. So I came up with an idea that it teaches them a lot of things, actually. And that is called smart proxy modeling. Smart proxy modeling is AI, and actually I just wrote a book on that, and the book is going to be published in October by CRC. And I can show you that the detail. I can give you a whole new, I do teach 2 courses on that to my kids. So what is that? The way I came up with that, first and foremost, to be honest, I came up with that by consulting with the company that's called ADNOC today in United Arab Emirates. At the time, what's called ADCO. And we did something, and what we did, we published it. I can send you the paper, SPE paper. What we did, after 5 years, it brought them about $2 billion extra production from a particular field. And in that, we worked with ExxonMobil, BP, and Shell. Those were part of that thing. And everything is there. And it has the same idea, because at that time, it was in 2005. At that time, it was all about numerical simulation, not about AI-based modeling. So what is that? And that's how I came up with this idea to teach my kids, my students. The thing is, you take a numerical reservoir simulator and you build a proxy model of the numerical simulator using AI. Now, you know what proxy modeling is, correct? The proxy modeling has been around for 50 years. There are 2 kinds of proxy modeling. One is called reduced order model, ROM. The other one is called response surface model, RSM. The reduced order model is physics-based, and the other one, response surface, is statistics. And actually, if you work with CMG and Eclipse and T-Navigator right now, the commercial, they all have response surface model as part of it. They allow you to do that inside the model. However, there are problems with response surface model, and there are problems with reduced order model, those proxy models. They made a lot of simplifications, the assumptions, a lot of that, but they make the model to run much, much faster, and you can run it hundreds of times very, very quickly, but you're solving a different problem. What AI-based model that we developed, what it does, let's assume that you have a numerical simulator and you run it on HPC, high performance computing, just 40 computers, right? And let's say you have 50 million cells in that numerical reservoir simulator. And when you run that on an HPC, it takes you 20 hours or 24 hours to make one run, right? We take the same model, we build an AI-based proxy of it, using artificial intelligence and machine learning. I can go into a lot of detail and all the details in that book. And then what happens, we make that, and the accuracy is over 95% at every cell. If you have 5 million cells, at every cell, the pressure saturation for that cell, for every time step, AI, smart proxy comes with over 95% accuracy. With that said, you know how long does it take for you to run the smart proxy? 5 minutes on your laptop, not HPC, 20 hours. That's why you can take your numerical simulation, run it 10,000 times and get a result. This helps you history matching. It has completely automated history matching very, very quickly. It can do optimization. It can do uncertainty quantification, but keep one thing in mind. It is as good as your numerical simulation. If your numerical simulation is fantastic, your smart proxy is fantastic. If your numerical simulation is not good, the smart proxy is not good. So it's not it's the same thing, but it makes it fast, and it make it run so much that you can history match it quickly, and you can use it to do optimization. You can actually change things very, very quickly to find out what's wrong with it. So in the university, you do this, but if when we do it for a company, then because they have the data, in actual data, we show them how AI-based reservoir modeling is. That's the difference.
I think it was more useful to know how we can start and how we can get the correct data. So we can start now taking questions from our students on the chat. So Engineer Ibrahim Ahmed asked, as a fresh graduate geophysicist, I really want to learn about fault detection using AI, but I don't know how to start in machine learning and tooling for that application.
To be honest with you, I didn't get it. Can you show me which one it is? It is in the chat, right?
Ibrahim Ahmed. First question in the chat.
Okay, what is the time of that? 10:41?
It was 4:45. 4:45.
Okay, Ibrahim Ahmed?
Yeah, that's right.
So, well, as a fresh graduate geologist, I really want to learn about fault detection using AI, but I don't know how to start in machine learning and linking for that application. So to be very honest with you, it's not going to, I don't know that because I'm not a geologist, but if we have done geologic work as well, but for that I need to literally go to the detail with the geologists and then help them in that. So I don't remember what fault detection. The fault detection, you mean the data fault detection, identification of what the data problem is? Is that what you mean by fault detection? So in that case, I could tell you again. It all comes to data. What we call, it's called a descriptive analytics. Literally, you take overwhelming majority of the time, you try to learn as much as possible about the data, and to learn. Because if you cannot learn the data, there is no way for you to do anything with the data. That's why your domain expertise is incredibly important to all go to. And to be very honest, that there is another question about YouTube. If you put my name on YouTube, you find a lot of lectures online that I have done, and you can listen to them.
Yeah, okay, thanks about this. So another question from Muhammad, 520 at 520. What about ML in energy efficiency, as it's the new strategy for the petroleum sector?
For petroleum sector?
Yeah.
1052, you said?
Then, sorry, 520. It was 520 from Muhammad.
Okay, 1 second, sorry. Muhammad, okay. What about machine learning in energy efficiency, as it is the new strategy of the, okay. Actually, the new thing, the efficiency of energy literally has a lot to do with what we call CCS analytics, which is, by the way, there is another book that I can show you. We have written on that, data-driven analytics. Let me show you this. These are the other 2 books that I have written. This is data-driven analytics for the geological storage of CO2. And some of the smart props is part of this as well. And literally right now, this carbon capture and storage become a very, very important thing. And the best way that we are using it right now, as you know, the carbon capture and the carbon storage and the efficiency of the energy has to do with the I think that's what you mean, has to do with the CCS, with the climate change. Right now, the book that I have written right now, Smart Proxy, has a lot to do with that. And literally, there are 2 ways of handling it. It all depends. The injection of the CO2 or the storage of CO2 takes place. It could takes into 2 general area. One, it can be in a aquifer. The other one, it could be in emptied oil and gas reservoirs, and they have 2 different areas. In 2 different areas, in emptied oil and gas reservoir has a lot of data. You can do a fantastic AI based, but in aquifer, since we haven't done anything with it, you don't have a lot of data. That's a whole different story that we are working on. That's a research mainly, more than anything else, that we can, if you want to have another short course that I teach on CCS analytics, we can talk about that if you
want. Great, okay. So about Assam Diab at 542, can you mention some applications of AI and ML in petroleum refining and petrochemical industry?
Not right now. Mainly, overwhelming majority of my work has to do with reservoir engineering, production engineering, and drilling to a certain extent. And the geological part of it has to do with reservoir, and that we do. So I still will be able, for many different companies, they come and tell questions very specific, and then we have to go and understand. What we do is we communicate, we go and work with their actual experts in that area that they're bringing up the question. And then we literally have to learn, because we are engineers, we are petroleum people, so it's not going to be hard for us to learn from them. But once we learn from them, then we find out how we can help them to solve it using AI. And another thing that we do is we very much try to understand how they're using it traditionally, engineering software. And then we try to find out what the problem is and how AI can enhance it. If we come to the conclusion, then we tell them. If we come to the conclusion that we don't know, we'll be very, very honest to them that we cannot do that, not right now. That's, to me, that would be a research, not a something that I have to do because I have done it. I know.
Okay, doctor. So another question from Muhammad Ramzi. He said, is data analysis is a gate to ML or to machine learning?
Absolutely, yes. Yes. And that's literally, they call so many different things with this different data scientists, data analytics, all of these, everything has to do with artificial intelligence and machine learning. If you do not use these two and you use the statistics, we've been using it for decades, right? We're using it for a century, and the results is what it, I'm not saying it's bad, but it's very, very different. I have lectures that I show the difference between the traditional statistics and AI and machine learning. There's a lot of difference between them. However, it's good for you to learn the statistics because that helps you in AI, but that's not exactly the same. They're very, very different.
So it's one of the pipeline, but there's related field, يعني not okay.
Exactly.
So can we recap about يعني on 2 minutes? Can we have a recap about ML and oil and gas on how to يعني really start or small roadmap for our students? How can they start?
So one of the things I can do, I'm going to type in the chat my email address. I just send you my email in the chat. It's shahab.mohaghegh@mail.wb.edu. Feel free to send me an email. I have what I call it, I have put together something that I call it artificial intelligence and machine learning in petroleum industry. But literally what it is, it's just a, bring it up. It's a AI and machine learning primer. It provides you a lot of links. It doesn't have anything, but it has hundreds of links. It tells you to videos, to papers, to lectures, all online, that you can go, and it provides you, to be very honest, it starts with different links, but take your time. It's going to take you years to do that, but do it. That's, to me, that's good information to get started with, to learn this technology in a real fashion, rather than in a fashion that people say, I can make you a data scientist in 1 month, give me enough money, I do that. That's literally not true. You can. Here, I'm sending it again. Oh, let me send it to everybody. Everyone. Sorry, I did only send it to one person. My bad. Now I send it to everyone. Sorry.
Never mind. As we respect your time, I totally appreciate you and your time that you are giving to us. I enjoy every minute of your lecture. Thanks for your passion and for your willingness to share that session with us today. And really, we are grateful. And the session wished that it lasts longer, but unfortunately, it's time.
Thank you. Thank you so very much. I wish you all the best. Let me know if there's anything I can do for you, okay?
Okay, bye-bye.
Bye-bye.
هنسيب إن شاء الله الميتنج مفتوح 5 دقايق بالظبط لحد ما الناس تملى الفورم. فورم الحضور موجودة في الشات بوكس.